Okay, so we were in the functional divisions of the cerebellum, which tell you are really the most important for you to feel really good about as a physical therapist, understanding the function. And so the functional divisions are these three regions: the vestibulocerebellum, which is synonymous with the floccular nodular lobe, also known as the archicerebellum. Then there's the spinocerebellum, which is synonymous with the vermal and paravermal regions, also known as the paleocerebellum. And then there's the cerebrocerebellum, which is synonymous with the cerebral hemispheres or the lateral hemispheres of the cerebellum, also known as the neocerebellum. Okay, so this one slide contains a lot of important information. So the vestibulocerebellum, it plays a role in influencing coordination of eye movements and postural movements, especially of the head and neck, because of its connections with the fastigial and vestibular nuclei. Okay, so the vestibulocerebellum, the Purkinje cells in the vestibular cerebellum, in the cortex of the vestibular cerebellum, they project to the fastigial nuclei, which are those deep cerebellar nuclei, and also the vestibular nuclei. The vestibular nuclei are almost like pseudo deep cerebellar nuclei. They don't mention, they're not actually they're not in the cerebellum, but Purkinje cells actually project directly to some of your vestibular nuclei. Okay, so, and then the vestibular nuclei and the fastigial nuclei, they then project to the vestibulospinal tracts to exert their influence for helping coordination of those muscles. Okay, so that's how they actually get your head and neck to be, to muscles to be dampened and work more smoothly and correct for any errors, is via their connections via the vestibulospinal tracts, which those mainly go up to your upper neck and back muscles, and they tend to be more bilateral in nature because you're having to co-contract and coordinate those muscles together more frequently. The spinocerebellum is the vermal and paravermal regions. The vermis, which is right in the center, that has to do more with coordination of the trunk, proximal limbs, and speech. Okay, right down the center. Think right down the center. Your mouth is right in the center of your body. Your spine and trunk right down the middle. It is most important for coordination of that, and it helps with limb coordination, but plays less of a role there. And the paravermal regions are your proximal limb musculature, your shoulder girdle, your kind of hips areas, those kind of things, the proximal limb musculature. It's important for coordinating those muscles. The spinal cerebellum, so the Purkinje cells in the spinal cerebellum and the cortex, they project to the fastigial nuclei as well as the interposed nuclei. The ones that are in the vermal region are going to project to that fastigial nucleus, this is right in the middle. The ones in the paravermal regions are going to go to the interposed, which is the globus and embelliform nuclei. Okay. And one of the, I posted some videos that I mentioned in an email yesterday about some resources, and one of the guys used this little memory thing for remembering the deep cerebellar nuclei. Is from outside to inside. It's don't eat greasy food. So it's dentate, embelliform, globus, and fastigial. Going from lateral to medial is how those are laid out. So don't eat greasy food. Then the fastigial and interposed nuclei that have been influenced by the Purkinje cell, they project axons to influence the vestibulo, reticulo, and rubrospinal tracts, as well as some projections up to the medial and lateral cortical spinal tracts. Because you'll notice this is influencing trunk, some limbs, some speech, and so it's going lots of places. You're getting both some proximal limb musculature, some trunk so these things project to some both medial activating pathways and lateral activating pathways to help correct movement in those. So it's pretty wide and diffuse, this vermal and paravermal regions. Then the cerebrocerebellum, this is for coordination of distal limb movement and motor planning and motor programming, especially movement sequences. The cerebrocerebellum projects to the dentate, okay? And then I should say, I don't have it on here. The dentate then will project to The lateral cortical spinal tract up in the cerebrum, they'll go up to the cerebrum to help influence the lateral cortical or cortical spinal tract that's going to come down. Also the rubrospinal tract, the lateral activating pathways that are going to more distal muscles. It's going to help to coordinate those. This is showing you how, this is a nice picture that's just color-coded and shows you how these different areas, what structures they project to or are related to. So if we, here's the vestibulocerebellum or floccular-nodular lobe. You'll see that it's the same color as their vestibular apparatus. So these guys work together. The vestibular apparatus and the floccular-nodular lobe or vestibulocerebellum are functionally related. The vermal and paravermal regions here, okay, the spinocerebellum, it influences descending spinal cord pathways, primarily medial activating pathways because it's mainly trunk and proximal musculature, but it also influences a few cortical spinal and lateral activating pathways as well, okay? And then the lateral hemispheres, right out here, it's mainly influencing, you know, motor areas up in the cortex and the lateral cortical spinal tract. It does influence the rubrospinal tract too, even though that's in the brain stem, but just this is showing generalities of how they, the functional relationship of what they connect to or what area they influence, okay? There's a kind of a somatotopic arrangement of your body. If you take kind of the look at the surface of the cerebellum, you're kind of laid out like this. So you see how you have in the center, in the vermal region, here's your mouth, you know, and here's your spine here. And then the flocculus, they don't show the vestibular apparatus associated with it, but here's your proximal muscles are here out in the paravermal region, and then your distal muscles are out in the lateral hemispheres, okay? So there's kind of like a homunculus on the cerebellum. There's some somatotopic arrangement to the cerebellum. So this is just showing you, so here's the floccular, this is the floccular nodular lobe here, and this would be a Purkinje cell sitting in the floccular nodular lobe. Actually, that would not be Purkinje cell, I'm sorry. Well, it could be. Or it could be the fastigial nucleus. It's more medial here. Actually, the fastigial nucleus is right in there. But these project directly to, some of your Purkinje cells actually project directly to the vestibular nuclei. Some of your Purkinje cells project to the fastigial nucleus, but then also project to your vestibular nuclei. There's a lot of bilateral connections there too. So they're influencing both vestibular nuclei on each side. You don't need to worry about with the cerebellum, contralateral, ipsilateral for these types of connections. You do need to understand it from a sensory standpoint that they are all ipsilateral, the spinal cerebellar pathways and so forth. So the only thing you have to remember about the cerebellum as far as dysfunction is if you have cerebellar damage on one side of the cerebellum, the same side of your body will demonstrate the impairment, okay, for the most part, especially limbs and so. And then this is the spinocerebellum. This is just showing, you know, this is kind of in the paravermal region here. This is a Purkinje cell in the cortex. It's going to come down and it's going to influence deep cerebellar nuclei, okay? Some of the embelliform and globose and embelliform nuclei, and some of those will project, some of those deep cerebellar nuclei will project up and influence some of the lateral cortical spinal tract fibers, but a majority of them are going to go down and project to reticulo, vestibulo tracts, those medial activating pathways in the brainstem, because this is more girdle and proximal muscles that it's going to help coordinate. Then this is the lateral hemisphere. Here's a Purkinje cell out in the cortex of the lateral hemisphere projecting to the dentate. Then the dentate's going to project to both the red nucleus right here. There's a little branch here going to the red nucleus, but then also has to go through the thalamus and go to the cortex up to the cortex to influence the descending lateral cortical spinal tract fibers. So if you have lesions of the cerebellum, if it's in the vestibulocerebellum, you're likely to see specifically nystagmus, eyes jumping around, looking uncoordinated when you ask them to move their eyes voluntarily. Look left, look right, and you see them kind of jumping because they're uncoordinated. They're not dampening their movements. You know, remember the cerebellum is really important for helping you initiate movement, then dampen it once you want to stop the movement. And if you don't have that dampening, your eye looks like it's shaking, okay? Because it's not this, you don't get this smooth dampening of ramping the eye movement up, then ramping it down as it gets to its end point. It goes, and it like jerks around because it's start-stop, has trouble coordinating. They also will feel disequilibrium. They'll feel dizzy, they may feel dizzy, and they'll feel like they can't keep their balance. They'll experience a sense of disequilibrium if they have damage to that vestibulocerebellum, because the vestibular system that tells you where your head is in space, that helps to communicates with your neck muscles, and then your cerebellum helps to make sure those neck muscles turn on and turn off in a smooth fashion. Their neck and head, this doesn't feel like it's working in conjunction with each other as well. Spinal cerebellum, if they have a lesion right down the center in that vermal region, you're going to notice a lot of trunkal ataxia. Like they just can't sit up straight, and when they walk, their trunk is really, you know, having a lot of ataxia, especially when you put them in a posture they have to maintain against gravity. Normally we have a little bit of sway and a little bit of air in our system, but our cerebellum helps dampen that and keep it in those. But if they're really struggling to fight it, they're going to have a lot of trunkal ataxia, okay? And then dysarthria. Dysarthria is going to be, they really have coordinating the muscles in their mouth is going to be hard for the same reasons. Paravermal region is going to be, they're going to have gait ataxia. So that's proximal muscles of the hip and so forth, trying to maintain that. When they walk, you're going to notice a lot of ataxia when they're walking. And then cerebrocerebellum is going to be limb ataxia, where you're going to notice this kind of stuff where they're really struggling with limb or their foot placement, and they try to put their foot down and they can't quite get it down and place it very well. So those of you that worked with Crystal in the pool or have seen her here, she has quite a bit. She's got actually some dysfunction in all. She's got lesions that involve all these areas, more so spinal and cerebro. She doesn't have nystagmus that's too bad or disequilibrium too bad, although she does experience it sometimes when I move her too quickly from, you know, sitting to sit, some supine to sitting and so forth. But she does have quite a bit of trunk ataxia. She's got dysarthria. She's got a significant amount of gait ataxia, and she's also got limb ataxia. So she's got lesions that are involved in multiple areas of her cerebellum. Yeah. Actually, it's that I don't know the root of the word, but it is not. Dysarthria is not, that arthria is not joint related. Yeah, it's a dysfunction or discoordination of the muscles that involves speech. So dysarthria of speech. Okay, yeah. No, there's arthritis, but arthria is a different. Yeah, I have to look up that Latin on that. So it's due to discoordination of the mouth. It's not a motor planning issue. That's an aphasia, where they have difficulty producing speech because they can't even think of how to form the word. They can form the word, but it doesn't sound right because the muscles are uncoordinated, and it makes it sound sloppy. But you know what they're trying to tell you, and they know, and they understand you, and so forth. You can have dysarthria with stroke, anything that affects the muscles, the coordination, or if they're weak in your mouth, soft palate, your tongue. If any of those are weak, you can have dysarthria. You can have both aphasia and dysarthria. You know, if you have a big lesion in your left hemisphere that affects the speech centers in your brain, which we'll get to later, plus affects the muscles on the right side of your face, you can be both aphasic and dysarthric. But in the case of a cerebellum, you're only going to be dysarthric if it's affecting that, you know, spinocerebellum vermal region. impairments associated with cerebellar lesions. So some of the terms that are commonly used, so there's ataxia. It's a catch-all term for lack of coordination, okay, is this term ataxia. And I tend to reserve the form ataxia if I feel or if I see true cerebellar involvement. I rarely tell somebody with a stroke in the cerebrum they have an ataxic movement. It's a spastic, it might be a spastic movement, it might be uncoordinated because it's spastic or they have synergistic movement, but it's not the characteristic ataxia, which usually includes some of these things. Dysmetria. Dysmetria is common with ataxia where they have inability to accurately move an intended distance. That your patients can have both hyper and hypometria, which means they undershoot or overshoot. So they're trying to, when you have them point to your finger, point to my finger, they might go past it or they might stop short of it, but they just have a hard time stopping right where they're supposed to. They'll go, ugh. And it's because your cerebellum is really important for slowing down and approximating your muscles as they get near a target. And the nearer they get, it's weird watching them, they'll go from here to here pretty good because that's a very gross movement, but once you get in here, your cerebellum really kicks in to fine-tune, to land your finger on your nose, so it gets worse the closer they get because your cerebellum is working hard, but it doesn't have the resources to do it, and it starts getting worse the closer they get to the target. Dysdiadochokinesia, that's a mouthful. So dysdiadochokinesia, it just means the inability, the lack of, or the inability to do both limbs in a coordinated movement, kinesia. So dysdiadochokinesia, it's inability to do rapid alternating movements. And so one of the tests we do is have them put their hands on their lap and say, turn your hands over as fast as you can. Some people do it where they have one hand like this and they go like this. Doesn't really matter. I just usually start with both palms up and just turn them over as fast as you can. You're comparing left to right. But if they've got bilateral involvement, you're going to see problems where they'll have slowness of that movement, or it breaks down, it deteriorates very quickly. They'll do a few good ones, and then and they can't quite figure it out. Those can be a symptom of cerebellar disorders. Action tremor versus a resting tremor. So Parkinson has a resting tremor. When they're at rest, their hand shakes, but when you ask them to point to their nose, it's smooth. It might be slow, but it's smooth. People with cerebellar disorders have the opposite. If their hands are at rest on their lap, they're fine. But as soon as you tell them to move, with action, it gets worse. And the closer they get to the target, it gets worse. So that's what we mean by an action tremor versus a resting tremor. It's not a true tremor. It's a form of ataxia, but it looks like a tremor because it's doing this, but it's only during action. At rest, they're fine. So that helps you figure that out. People with cerebellar lesions typically don't have frank weakness of any kind. They don't have hemiparesis. However, the cerebellum plays some role in modulating overall tone and muscle force in addition to the basal ganglia. And you might see a little bit of hypotonia on the side of involvement. So the muscle tone will be just a little lower. They might have a subtle weakness on that side, but it's not anything profound. You got to really kind of work at it to feel it or pick it up. You got to be good at it to kind of pick it up. So it's not uncommon to have a little hypotonia. This picture is in your book, and it's actually a really kind of if you really kind of appreciate this picture, it really shows the entire motor system, including the basal ganglia and the cerebellum, all your descending motor pathways and so forth, all in kind of one picture. And so it's kind of a whole, it's kind of a lot to take in, but, starting up at the top, you have, this is your motor cortex and premotor, supplementary, and primary motor cortices, okay? And then you look where they have their projections to, You obviously send projections down to the putamen. You could put caudate in here too, caudate, because you project to the striatum, right? You project down to the striatum, to the basal ganglia circuitry, okay? This is the loop right here. This is the loop through the basal ganglia. From that, through that, to the motor thalamus, both direct and indirect loops. They don't show both of them. They're just showing you the general connections. And this is the basal ganglia loop right there, is what you're seeing there. Your cortex projects to the red nucleus. The rubrospinal tract area here is the rubrospinal tract. You have the lateral cortical spinal tract that goes to the lateral. These are going to the lateral motor neuron pool, which are more for distal fractionated types of movements. This is fractionated movement. This would be upper limb. This should say, I don't know why it says extension. This should be flexion. Upper limb flexion for the rubrospinal tract. I don't know if that's in your, is that in your 5th edition still like that? We'll have to, well, you can check and see. I think I took this picture from the 4th edition. I don't know if they corrected it for the 5th edition. These are the connections of the basal ganglia with, this is the pedunculopontine nucleus in the brainstem. We did not mention this. This is the midbrain locomotor, is like a locomotive center that helps like promote walking. I didn't even mention that. So there is a center in your brain that your basal ganglia helps to kind of facilitate when you just want to walk, and it's kind of an automatic locomotion center. Don't worry about it for an exam or anything. You just want to point that out. That's what that MLR is. These then connect with the reticular formation where your reticulospinal tracts are that influence the reticulospinal pathways for postural and girdle muscles and so forth, which are all part of this medial motor neuron pool, which these are all the things that the median motor neuron pool, those reticulo and vestibulospinal tracts all tend to influence, okay? All those functions. We have our cerebellum here, which our cerebellum has projections to vestibular nuclei, directly to some vestibular nuclei. Here's our medial cortical spinal tract projecting down from here to the medial motor neuron pool. Cerebellum also communicates back up to the motor cortex to help influence the next signal coming down via the thalamus, goes back up to the motor cortex. Oh, crap. No. Okay. So this is showing you, and then when this is the pathway, the copy of your message, of your motor message that goes through the pons we showed you, and then goes to the cerebellum. That delivers the copy of the message to the cerebellum. The thing they don't show in here is the olive, the inferior olives also project up to the cerebellum via those climbing fibers. So if pictures help you, this might be somewhat helpful. I want to just go back here real quick. And again, just kind of draw out on here what happens with the cerebellar connections. And I'm going to draw that same one out that we did mainly for voluntary motor activity. Okay, but it's the same kind of process that happens for postural girdle muscles and vestibular input. But let's just kind of draw that out again. So you're going to make a voluntary movement, right? It's going to start up here in the premotor, supplementary motor area, kind of the motor planning area, right? Typically. It's going to go through the basal ganglia. And if your basal ganglia decides it's an activity that wants to occur at a certain level of force, a certain sequence of muscles that have to occur to do this, that signal will go through the basal ganglia to the thalamus, then project back up to the cortex to finally then release a signal from, so this would be motor planning areas up here, motor planning. And this would be better to show you on a side view of the brain, but just work with me here. This is motor planning. This would be your primary motor strip here. It's going to go to the actual muscles. So the primary motor strip is projecting this corticospinal tract fiber here, right? It's going to go down from your corona radiata to your internal capsule. It's going to come down the front part of your midbrain in the crus cerebri. And then once it gets to the pons, some of those will continue on, but you're going to have a few fibers that branch off from that are going to communicate with a pontine nuclei. And these fibers are the corticopontine fibers. And these are the pontine nuclei, which are then going to send an axon via the middle cerebellar peduncle. That's how they're going to get into the cerebellum to the cortex of the cerebellum. So that's delivering the copy of that message you're going to send down to that muscle via the corticospinal tract. It's going to deliver a copy of that. This is going to come down. It's going to cross over in the lower part of the medulla in the decussation of the pyramids as the corticospinal tract, and then go down. And this will happen to go to, we're going to go to a leg out here. We're going to go to the foot out here on, this will be a left leg. This is starting on the right side, where this thing's looking out at you. This is, you know, right and left on there. So it's going to go to their left leg, let's say. Okay. So your left leg starts moving or doing something, and now your muscle spindles, your joint receptors in the leg, because it's moving, are now sending back sensory information. Some of that you're consciously aware of, but a big portion of it is unconscious, and that's going to your cerebellum. So those are going to come up via, we're just going to collectively right now, at this point, for this exam, you can pretty much know them collectively as the spinocerebellar tracts. So the spinocerebellar tracts are going to come up, bringing that information from the muscle spindles and joint receptors. They're going to come in via the inferior, this is the inferior cerebellar peduncle, the ICP. They're going to come in and they're going to deliver that same, or they're going to give a report on what actually happened. You send a signal to tell the leg to do this. Did it really do what you said it to do? You know, did it encounter some new environmental constraint, or was what you did? Were you standing on a surface that was softer than you thought it was, or was the ball you were kicking heavier than you thought it was, and that changed the dynamic of the task? And so, you know, when you sent this signal coming from the motor, the copy of the motor message, that changed the sensitivity and the frequency of the inhibitory stimulus of the Purkinje cell. And then when you send this impulse back, it reports back and says, did these messages match each other? And if they didn't match each other, we need to tell that Purkinje cell to influence and send a signal to the deep cerebellar nuclei. So in this case, this is a lateral hemisphere, right? And so there's a deep cerebellar nuclei in there that's going to project to, which is what? If it's lateral, dentate. So here's our dentate out here, kind of squiggly thing here. And so this Purkinje cell sitting in here is going to project to the dentate. And it's taking that information basically, and it's encoding it by changing its frequency of how strong it's going to send an inhibitory impulse back to the dentate based on the influence of those two signals that arrived right near it in that discrete little zone that is being packaged, and we know it's coming from that little part of our ankle or that foot because the stimuli don't spread because those parallel fibers and all those inhibitory interneurons in the cortex of the cerebellum don't allow the signal to spread. And so we can send this discrete signal back to the dentate, and then the dentate will project from here. It'll back through, actually it'll probably come up through the superior cerebellar peduncle, to go back up, and it's got to stop at the thalamus in the VA or the VL of the thalamus, the ventral anterior ventral lateral parts of the thalamus. It's going to synapse there, and then this signal then will go back up to the motor cortex to influence the next signal you send down to adjust the activity, to dampen it, to speed it up, to change the force you're using with that next signal. And that same process happens whether it's the vestibular system. Your vestibular apparatus, as your head is moving in space, sends a signal to the cerebellum, but then your neck muscles and your joints in your neck start moving, and they send a signal back through spinal cerebellar tracts back into the cerebellum. And the cerebellum says, "Oh, did the information from our vestibular system match the information come from our joint receptors and our muscles in our neck? And if they don't match, then I need to make an adjustment," and the Purkinje cell sends a signal back to some of the fastigial nuclei and vestibular nuclei to change the activity in the vestibulospinal tracts to the next signal to ramp it up, ramp it down, tune it up, tune it down, that kind of stuff. Does that help? I wish I could draw better. I really do. Problem with this drawing is I can't place the heel of my hand on here, so I'm drawing like this, and I wish I had a I'm sure the iPad or something might be better where I could actually lay my hand on it without it influencing. This is a touch screen, so I'm just trying to draw like a little kid up here. Um, yeah.
Because mine has the option to draw with touch.
To do what?
You can like disable draw with touch, so then like when I put my hand on it, it doesn't draw unless it's with a pen.
Oh, really? But you have. Oh, I have this pen. So, but you're using a Microsoft, right? Yeah. Yeah. I'll have to try that. Learn something new. So that is that. Any questions? Watch those videos that I posted. They're all good in different ways that'll give you some appreciation. There's lots of great YouTube videos out there. I have to really read lots of things, watch lots of things. I get a little bit different perspective from each of those. Then it all starts to make sense to me because I pick up something that works for me from each video. Not any one person's explanation works for me. One part of that explanation worked for this video, and then another video was better at this little explanation, and all of a sudden it starts to gel for me. All right, let's do this.